Part 2 is reactions in TCA cycle. So Kreb cycle or TCA cycle, it has 8 steps or 8 reactions. First step is the formation of citrate. Second step is the isomerization of citrate to isocitrate. Step number 3 is the formation of alpha ketoglutarate and carbon dioxide. So this is the first oxidation decarboxylation reaction. Step number 4 is the formation of succinyl-CoA and carbon dioxide. And this is a second oxidation decarboxylation reaction. Step number 5 is the formation of succinate. And step number 6, formation of fumarate, which is a FAD-linked oxidation reaction. Step number 7 is the formation of L-malate. And final step, step number 8 is the regeneration of oxaloacetate, which is a final oxidative step. So these are the 8 steps reaction in Kreb cycle. So this is the reaction of the TCA cycle. Similar with the previous slide, it shows the reaction of cycle with the substrate and the products. So for example, here step number 1 is acetyl-CoA plus oxaloacetate and water molecule to produce citrate and coenzyme ASH. With the enzyme catalyze this reaction is citrate synthase. And step number 2, from citrate to isocitrate catalyzed by aconitase. Step number 3 is isocitrate and NAD plus catalyzed by isocitrate dehydrogenase to produce alpha ketoglutarate and NADH and carbon dioxide molecule and H plus ion. Step number 4 is alpha ketoglutarate plus NAD plus coenzyme ASH catalyzed by alpha ketoglutarate dehydrogenase producing succinyl-CoA, NADH, carbon dioxide and H plus ion. Step number 5 is succinyl-CoA plus GDP and inorganic phosphate catalyzed by succinyl-CoA synthetase and produce succinate, GTP and coenzyme ASH. Step number 6 is succinate and FAD catalyzed by succinase dehydrogenase in producing fumarate and FADH2 molecule. Step number 7 is fumarate and water molecule produce L-malate catalyzed by enzyme fumarase. And final step is how L-malate and NAD plus produce oxaloacetate and NADH and H plus ion, which catalyzed by malate dehydrogenase. So now we are going to look into the individual reactions of TCA cycle. So in the first step, there is a condensation of acetyl-CoA with oxaloacetate to form citrate. So this reaction is basically a exergonic reaction where it releases energy. So for the overall reactions, oxaloacetate 4-carbon molecule plus acetyl-CoA plus 1 molecule of water catalyzed by citrate synthase will produce citrate molecule plus coenzyme ASH. But initially, this reaction consists of 2 steps. This reaction itself consists of 2 steps. The first steps produce a cityl coenzyme A complex via aldol condensations. And the second steps release the coenzyme A to form citrate via hydrolysis reaction. So basically the second step reaction, it breaks a high energy thioester bond and thus it drives this overall reaction. So what is thioester bond? Thioester bond is between coenzyme ASH and the methyl groups of acetyl-CoA. And then that is why this overall reaction it consists of water molecule because of the second step, the hydrolysis reaction. So basically, the first step is oxaloacetate plus acetyl-CoA producing citryl-CoA. And the second step in this reaction is basically citryl coenzyme A plus water molecule producing citrate. So this reaction is basically here catalyzed by citrate synthase where this enzyme is allosteric enzyme that is inhibited by molecule NADH, ATP and succinyl CoA. So here in this first step, once citrate is formed, it must be converted to the isocitrate isomer. So for step number 2, once citrate is formed in step number 1, it must be converted to the isocitrate isomer. So this citrate is isomerized to isocitrate and the reaction is catalyzed by aconitrase. So this is the individual reaction, the figure. So hydroxyl group in the left side in citrate molecule is moved from carbon number 3 to carbon number 2. These steps also it involves two processes. One is dehydration, which we remove one water molecule, followed by second reaction, which is hydration reaction, as it use other water molecule to replace hydroxyl ion at carbon number 2 and hydrogen at carbon number 3. So basically in these reactions, citrate molecule will remove one water molecule, producing cis isonitrate, which is enzyme bound substrate. So when we remove water molecule at carbon number 2 and carbon number 3, okay, after we produce cis aconitate, another hydration reaction where we add in water molecule. So we add OH carboxyl at carbon number 2 and hydrogen at carbon number 3 producing isocitrate. Nothing much change in this reaction except for carboxyl group OH and except for hydroxyl group OH and hydrogen ion. So for step number 3 also consists of two processes. So in this step, there are oxidation of isocitrate followed by decarboxylation to form alpha ketoglutarate and carbon dioxide. So whenever carbon dioxide is being released, we call them as decarboxylation reaction. So the first reaction it involves the abstraction of a pair of high energy electron to form high energy intermediate oxalosuccinate. So remember that oxalosuccinate is a high energy intermediate. So this oxalosuccinate, when it has high energy, it is because this structure is very unstable. Okay, so that is the first reaction in this step. Second reaction is the decarboxylation reaction. So this reaction is catalyzed by isocitrate dehydrogenase, which is an allosteric enzyme. So when we say about allosteric enzyme, we must have inhibitor and activator. So here the inhibitor is ATP and NADH and activator is ADP and NAD+. So it depends on how high the level of those substrate. Okay, when we say about the electron abstraction of a pair of electron, here is two electron is being removed from the 6 carbon molecule. Okay, these 2 electron then being accepted by NAD plus to produce NADH plus H plus. So we lost 2 hydrogen in the 6 carbon initial molecule, okay, to produce oxalosuccinate. And later on, this oxalosuccinate lost this CO2, okay, as you can see in this figure, and producing 5 carbon molecule alpha ketoglutarate. So the first reaction is the loss of electron, where NAD plus receive 2 H plus. And the second reaction is the carboxylation, where oxalosuccinate lost 1 molecule of carbon dioxide, producing 5 carbons alpha ketoglutarate. So the net reaction here is isocitrate plus NAD plus, producing alpha ketoglutarate plus NADH and 1 molecule of carbon dioxide. So in step number 4 is the oxidative decarboxylation of alpha ketoglutarate to succinyl-CoA. So this reaction is catalyzed by alpha ketoglutarate dehydrogenase complex, which is like pyruvate dehydrogenase, is a multi-enzyme complex and require coenzyme A, thymine pyrophosphate TPP, lipoic acid, FAD, and NAD+. So similar with pyruvate dehydrogenase reaction, this alpha ketoglutarate dehydrogenase complex also react similarly with pyruvate dehydrogenase. So basically, this reaction is quite similar with pyruvate carboxylation reaction. So we have learned about pyruvate carboxylation in part 1. So I won't explain further about this reaction. So basically in this reaction, what I want to highlight is, remember coenzyme ASH here, okay, producing carbon dioxide, and NAD plus accept electron, 2 electron here, producing NADH plus H plus. So the reaction here produce succinyl-CoA. So how coenzyme A accept the molecule, and how NAD plus accept the electron, okay, and being reduced to NADH plus H plus. So the information or the explanation are similar with the reaction in pyruvate carboxylation. In step 5, the thioester bond, which has high energy, of succinyl-CoA is hydrolyzed in the formation of succinate. As you can see here in the figure of succinyl-CoA molecule, the bond in red box here is the thioester bond, which has high energy. So it is very exergonic. But then when this reaction needs to attach a phosphor group, this reaction is endergonic, where it needs a lot of energy. So when we couple these two reactions, the energy released from the thioester bond can be used by the GDP when it needs to be attached to the molecule. So here, before that, the 2 carbon which attach to the carboxyl group of succinate, they are basically equivalent. So this is the first energy yielding step of the cycle. So this overall reaction is slightly exergonic as energy is being used to attach a phosphor group onto a GDP to form GTP. So this is what I'm talking about. So why it is slightly exergonic? although we have thioester bond which has high energy, because that energy is being used to attach a phosphor group onto a GDP to form GTP. So basically this is a phosphorylation reaction. So here the net reaction produce GTP and coenzyme A SH, as in the red box on your right hand side in this figure. So this coenzyme A SH is being regenerated, so it can be used again later on, especially in pyruvate carboxylation. Okay, step number 6. This is an oxidation reduction reaction that oxidize succinate into fumarate while abstracting 2 hydrogen ion and a pair of electron. And in the process, it reduces FAD into FADH2. So this hydrogen ion, this hydrogen ion is being accepted by FADH and produce FADH2 in the process. So FADH2 here is bound to the enzyme and can be passed to the electron and continue electron transport chain later on after TCA cycle. So this is the what we call as uh, how they are together. Okay, how TCA and ETC works together as well. How they are connected. So this succinate, it gives electrons, okay, and abstract 2 hydrogen ions, giving them to FAD, producing FADH2. This FADH2 that is bound to the enzyme, okay, will pass the electron during the ETC reaction. Okay, this is basically the step number 6, formation of fumarate. Okay, step number 7 is the hydration reaction. The hydration of fumarate, which is only in the L form, can occur. So in the red box here, water attacks only at a specific site. So only at the L isomer of malate can be formed. So here is the how water attack this specific site, and this specific site at fumarate molecule and produce L-malate molecule. So this is step number 7. Step number 8 is where malate is oxidized to oxaloacetate and we regenerate the oxaloacetate. So this is the final step. So malate dehydrogenase, it oxidizes the malate into oxalate and transfer the electron onto NADH. So when we talk about electron, whenever there's a transfer of electron, we also transfer of hydrogen ion. Because they are together. So this process is very endergonic, which require energy. So it must be coupled with other exergonic steps that can release and provide the energy. So in this step, since it is endergonic, it has to couple with other reaction that is exergonic. So basically this is and other steps are actually step number 1 in TCA cycle, which are exergonic. So then this step and step number 1 can be coupled together. So as soon as the cell produce oxaloacetate is used in step number 1. So the energy release is used in step number 8. So this is how they are connected. In addition, NADH2 molecule that is oxidized in ETC, electron transport chain, also are used to drive this particular reaction in step number 8. So basically that is how the reaction in step number 8, which is endergonic, gets the energy to drive this pathway. One is from energy release in step number 1 of TCA cycle, and another one is NADH2 molecule that is oxidized in ETC, which are also hexagonic. They are both used to drive this reaction in step number 8. So here the net reaction would be L-malate and NAD plus being reduced to NADH and H plus, as well as producing oxaloacetate. So in this reaction, the final stages of citric acid cycle or TCA cycle, we produce FADH2, we produce one molecule of NADH during malate to oxaloacetate, and FADH2 during succinate to fumarate, and the oxidation of pyruvate. So the oxidation of pyruvate, it forms CO2 molecule and ATP. So from pyruvate dehydrogenase complex during pyruvate decarboxylation, pyruvate and coenzyme ASH plus NAD plus producing acetyl-CoA and NADH and one molecule of carbon dioxide and hydrogen ion. And when it enters TCA cycle, we have molecule of acetyl-CoA, 3 NAD plus, and FAD plus GDP plus inorganic phosphate and 2 molecule of water, and produce 2 molecule of carbon dioxide and coenzyme ASH and 3 NADH plus 3H plus FADH2 and 1 molecule of GTP. So basically from these two reaction, for overall reaction is pyruvate, and for NAD plus, 1 molecule of FAD, 1 molecule of GDP and inorganic phosphate, and 2 molecule of water. Produce 3 molecule of carbon dioxide and 4 molecule of NADH and 1 molecule of FADH2 and GTP, as well as 4 hydrogen ion. So eventually 1 ATP production per 1 molecule of pyruvate here. Okay, for NADH will produce 10 ATP. When we take into account 1 ATP is 2.5 for each molecule of NADH. And we also produce 1 FADH2 if we take into account 1 ATP with 1.5 for 1 molecule of FADH2 and 1 GTP, which is equivalent to the 1 molecule of ATP. So here a total of 12.5 ATP per molecule of pyruvate, or 25 ATP per 1 molecule of glucose will be produced. So basically this is the overview of the cycle. We can start from the pyruvate molecule up there from glycolysis, and before it enter acetyl-CoA, there's a pyruvate carboxylation reaction first will occur, and then it will enter TCA cycle in the form of acetyl-CoA. The changes of carbon from step number 1 to step number 8 of TCA cycle. So in the red box here is where NADH molecule being produced, and in green box here is FADH2 being produced and 1 molecule of GTP in blue box here. So ATP generation both in glycolysis and Krebs cycle, it will produce 25 ATP molecule per 1 6 carbon molecule of glucose. So in the glycolysis, 1 ATP molecule per 3 carbon glyceraldehyde 6-phosphate. So here we produce, since glucose is 6 carbon, so in glycolysis, at the end we have 3 carbon molecule, which is glyceraldehyde 6-phosphate. So we're producing 2 molecule of pyruvate. So here 2 ATP molecule per 6 carbon glucose, 2 NADH molecule per 6 carbon glucose, and the total of 5 ATP molecule for 6 carbon glucose. So total 7 ATP molecule for 1 molecule of 6 carbon glucose. So when we add up together glycolysis and Krebs cycle, how much ATP they produce are 32 ATP molecules. So this is how ATP generation in glycolysis and Krebs cycle. So the glucose molecule produce 2 NADH. So from 2 NADH, we produce 5 ATPs. And at the end, we produce 2 pyruvate molecule of glycolysis. So from 2 pyruvate molecule, we have 2 NADH, which is equivalent to 5 ATP. So when it enters TCA cycle, in TCA cycle, we produce 6 NADH, 2 FADH2, and 2 GTP. So this 6 NADH we produce 15 ATP, 2 FADH2 produce 3 ATP, and 2 GTP we produce 2 or equivalent to 2 ATP. To summarize everything, okay, in the TCA cycle and pyruvate dehydrogenase reaction, 1 molecule of pyruvate is oxidized to 3 molecule of carbon dioxide. So this one includes 1 molecule before entering TCA and 2 itself in TCA cycle as a result of oxidative decarboxylation. And then this oxidation are accompanied by reduction reaction, which involve NAD plus to NADH, FAD to FADH2, and also GDP is phosphorylated to GTP. So this one we have seen earlier. So the overall 8 steps or 8 reaction in Krebs cycle. With that, we end part 2 of TCA cycle.